David Smith here with one more flipped classroom math video for your enjoyment. 3 tips. First, you can speed up or slow down the playback if that helps you follow along. Second, you can pause anytime to catch up with your notes or think a little harder. Lastly, you could turn on the captions, which will show you my words on the screen below. Today's video covers exponential growth and exponential decay. And these are key concepts that come up in science a lot. So let's take a look at that. Now, exponential growth is a certain kind of a growth where something is getting bigger and bigger and bigger, or a population is getting bigger and larger. So I want you to pause the video and think real hard for a minute about what is exponential growth. We know what growth is, but exponential growth is a special kind of growth. So think about that for a second. All right, if you came up with something that relates to the growth rate, you're on the right track. Exponential growth is growth that increases its rate. So over time, you add more and more and more each time step. So like the first year, you might add 20 of them. The second year, you might add 25. The third year, you might add 31. Fourth year, and so on and so forth. So the rate is not fixed. The rate is increasing. How about exponential decay? So now that we've talked about growth, you could probably figure out what decay is. But pause the video for a second, think about that. All right, let's see how you did. Exponential decay, this is something that's lowering, that's decreasing. It has a rate of decay that itself decreases. So we might talk about like a half-life. Like carbon-14 has a half-life of maybe 6,000 years. So that means that every 6,000 years, there's half as much left as you had before. So the first 6,000 years, you've got half. But then the second 6,000 years, you've got half of that half. So you only lost a quarter of your original amount, and then an eighth, and then a 16th. So over time, the amount you're losing to decay is decreasing, okay? So these are the key concepts between exponential growth and exponential decay. Now I want you to think real hard. What might an equation look like that would model either exponential growth or exponential decay? Think about that, maybe jot down a couple equations that might do that for you. Okay, an exponential equation is defined fairly simply. It has a variable in the exponent. So we haven't done that in class. So when you have a variable in the exponent, it's called an exponential equation. So I put 2 examples here. This is population as a function of time would be 1.15 raised to the number of years, for example, like raised to the t power. So this would be an exponential growth equation, perhaps for population. This would be mass as a function of time, maybe for carbon-14 decaying, and it's 0.095 raised to the t power. So each year you're going to have 0.95 of what you had the last year. So every year it's decreasing. So this one's for exponential growth, this one's for exponential decay. Let's do a few examples. All right, let's take a look at an exponential equation. This time we're going to model the growth of rabbit populations. Now we all know rabbits breed quickly. Put 2 rabbits in a pen, give them enough food and water, and come back several weeks and several weeks and several weeks later, you're going to notice there's a lot more rabbits in that pen. In fact, they are growing exponentially. And let's take a look at how that might work with mathematics. So here is an equation that might model that situation. We have 50 times 1.07 to the n power. R is the number of rabbits. So that's what our equation tells us is the number of rabbits. And n would be the number of weeks. So as this experiment goes down the timeline, weeks keep adding up. We're going to put a bigger and bigger number in there for n. And since this number is bigger than 1, it's going to cause the thing to grow. It's going to cause the population to grow. So let's generate some numbers using this equation. So here's the question. How many rabbits after 0 weeks? Now look at that equation. You can do this really quick and you don't need a calculator. Okay, let's see how you did. Here's my plug-in step for 0 weeks. 50 times 1.07 to the 0 power. And I just wrote 50, because that's correct. Remember your zero power rule, okay? Anything to the zero power is 1. So this term becomes 1 times 50 is 50. Now think about it for a minute. What does this question mean? What am I asking? How many rabbits after 0 weeks? We haven't started our experiment. What does that mean? Think about that. Okay, if you came up with this, you're right. 0 weeks is how many rabbits at the start. So before we start marching down the timeline, we have a certain amount of rabbits that we're starting with, and that would be 50. And so anytime you get a question like this and they ask you, what's the value at the 0 time number, you're always going to be this constant outside of the exponential part. Okay, good trick to know. You can always do your plug-in step and it will get you there, but sometimes it's good to be able to just understand how it works. Okay, so I want you to pause the video and do these 3 calcs, okay? Do it at 15 weeks, at 30 weeks, and at 45 weeks, and then come back. All right, I want you to check your work. I have my 3 plug-in steps, 50 times 1.07, raised to the 15 weeks for that one, raised to the 30 power for that one, and finally raised to the 45th power for that one. So that's how all the plugins go. And then I did my math, and I got 137 for 15 weeks, 380 for 30 weeks, and 1,050 for 45 weeks. That's a lot of rabbits. So what I want you to do is take a look at your numbers first. Actually, make sure you can get these calculations. So if you made some mistakes, pause the video and take a look at that and make sure you can get those correct. And then once you've done that, come back. Okay, so I want you to look at these 4 numbers and think about how that shows growth that's exponential and not linear. Linear growth would be just continuing at the same rate every time step. Notice how this is 15 weeks plus another 15 weeks plus another 15 weeks. So we're looking at constant time intervals, but the growth is exponential. So do a little bit of critical thinking and see if you can show me, even with numbers, how that growth is exponential. All right, check this out. I'm going to go over here and take a look. I made a new column for increase. So how much is it increasing by each 15 weeks? So in the first interval, going from 0 to 15 weeks, I get 137 minus our starting number. We had 137 at the end, so minus 50. We grew by 87 rabbits in 15 weeks. In the second time step, going from 15 to 30, we ended up with 380. So how many rabbits did we increase by? We increased by 380 minus 137, so we got 243 more rabbits. So quite a few more. And then finally going from 30 to 45 weeks, I did my math here, and we increased by 670 rabbits. Okay, so it's increasing at a quicker rate. So one more thing we can tease out of this data. What I want you to do is make a third column right there and figure out what is this rate. We increased by 87 rabbits in 15 weeks. What's the weekly rate for this period, and for that period, and for that period? There's a little bit of critical thinking there. I want you to pause the video, see what you get. All right, let's see how you did. Basically, a rate is the amount of change over the amount of time. That's what a rate is. So all I did is I divided the amount of change. We got 87 rabbits in our first time step, and we got them in 15 weeks. So dividing 87 by 15 gives us 5.8 rabbits per week. So that was our growth rate for the first 15 weeks. Rabbits per week is our unit. Rates always have units, don't forget those. Now moving along, going from week 15 to week 30, still 15 weeks, but this time we gained 243 rabbits. So our rate is 243 divided by 15, gives us 6.2 rabbits per week. So the rate is increasing. Finally, in our last one, again, we had 15 weeks, but this time we gained 670 rabbits, quite a bit more. So dividing 670 by 15 gives us 44.7 rabbits per week. So you can see the rate of growth is increasing, hence exponential growth. So now what I want you to do is pause the video and make a graph. Your graph should be, I'll do a little quick one right here, should be weeks here, and the number of rabbits there. So pause the video and use this data here, the number of weeks and the number of rabbits, and make a graph that shows that. And pay attention, scale your axis evenly, and then draw your line connecting your 4 data points. All right, let's see how you did. I'm going to break this down a little bit because it always helps to have a little bit more instruction with graphing. I find that my students tend to struggle a little bit with making good graphs. So if you've completed yours, that's great. Just follow along and see how you did. So first off, here's my data. I simplified that, put them in a table. 0, 15, 30, 45 weeks, and the number of rabbits we have. Now here's my graph. Now scaling the axes is the thing that people struggle with. So on the horizontal axis, on the weeks, I'm going by 15s and I get to 45. So I'm going to have 1, 2, 3. The 0 weeks is right here. So I might go 15, 30, 45. And that I mark them evenly. That's all I need. So here's my 0, my 15, my 30, and my 45. I only marked what I needed. Okay, so I could go 5, 10, 15, 20, 25, 30, 35, 40. I could do that, but really all I need are these 15s. Okay? Now, if you haven't gotten this far yet, think about the vertical axis, the number of rabbits. How are you going to scale that one? Okay, the numbers are quite bigger. That one goes all the way to 1,050. So there's a pretty easy way to do this. I'm just going to mark the top value as 1,000, and then that last point is just going to be a little bit higher than that line. So now I'm just going to divide this up in a kind of convenient way. This would be 500, and maybe I could just go by hundreds now. So 100, 200, 300, 400, 600, 700, 800, 900. And that's a good vertical axis for the number of rabbits. So if you haven't gotten this far yet, go ahead and get that in your notes and then plot all those points and draw a line. All right, here are my 4 points. My 0, 50 rabbits, my 137, my 380, and finally my 1,050. Now, what do you notice about that graph? There's something interesting, and there's something that basically tells us that it's exponential growth. Think about that for a sec. Check it out. It's getting steeper and steeper. The slope is the growth rate. So the growth rate is increasing. So what we're going to say is the curve gets steeper, which means that the growth rate is faster. Growth rate increasing. Okay? So there you go. That's a nice example that shows all the key features of exponential growth. Now let's move on to exponential decay. All right, let's look at decay. Now, if you recall from that first board, exponential decay is a situation where the rate of decay decreases over time. Okay, so let's do an example that shows that. So mathium is an element that I just invented that's a radioactive element that decays according to this equation. So a radioactive element that decays is basically just an element that's got an atomic structure that's not stable. Okay, so all the atoms in there, they're doing okay. They're saying, yeah, we're mathium, but it's just not terribly stable. So every so often, one of those elements goes, whoops, there goes an electron, or whoops, there goes a proton, or whoops, there goes a neutron, or something flies off that element, and it changes into something else. Either another isotope of the element, or it changes into another element. So that's what we say radioactive decay. It emits radioactivity, and what's left is a different element, basically, a different isotope or a different element altogether. So what we're saying is mathium, radioactive, it decays according to this equation. So W equals 2,000 times 0.89 to the M. W is the weight in grams of our sample of mathium. And M, the power, the exponential part of this, is millions of years. Okay, so it takes a long time for mathium to decay, but boy, it does decay. So notice how this number here is less than 1. So whenever you have your base for where your power is, if that base is less than 1, you know right away you have a situation with decay. Okay, So let's do some calcs. What is the weight of Mathium after 0 years? Now this one's really fast. I want you to just go ahead right now, just write down the answer in grams. You don't even need to do a plug-in step. Okay, I did my plug-in step just because I like to be thorough. So it's 2,000 from here times 0.89 from here to the M, to the millions of years. And this is after 0 years, so it's to the 0 power. So we have indeed 2,000 grams right there. Now what does this mean in terms of this equation? That's our starting point. So we turn the clock on right now. Our sample is 2,000 grams, and now we're gonna wait several million years. Obviously, we're not gonna be around for that, but we can measure these things at much smaller time intervals and know what would happen after a lot of time. So now I want you to pause the video and do these 5 calculations, and I know you can do it. All right, so I did a plug-in step for 10 million years, showed you how that works. Then I got on my calculator, I did the math. We have 624 grams after 10 million years. Now for the rest of these, I just did my calcs and wrote my results. You should know how to do this on your calculator, including raising a number to a power that you specify. There's keys on your calculator to let you do that. If you can't find it, talk to me in class, we'll get you going. So here are my results: 195, 61, 19, and 6. I rounded to the ones place. So I rounded away the decimal because I know that when I graph, the decimal's not gonna matter. My graph's not gonna be accurate enough for that. So here we go. 0, 10, 20, 30, 40, 50 million years. Not much left, right? We started with 2,000 grams. After 50 million years, we have 6 grams. That's a bunch of decay. Now, I want you to make a graph of this situation. And again, what we're gonna do is time is gonna be your independent variable. That's millions of years. And this is going to be your weight in grams. So I want you to pause the video and make a nice graph with scaled axes like we did in the last one, and then come back. All right, before we look at the graph, I want to show you my table that I made over here. I went ahead and transferred my data over. This is millions of years, that's the weight in grams. And those are the results of our calculation. The amount of decrease from 2,000 to 624 is 1376. So we lost that much in the first 10 million years. And then each time I calculated the loss by subtracting the previous one from the current one. And you can see that our decrease is decreasing. We're losing less and less each time interval. So the rate of decrease is itself decreasing. So there's our exponential decay shown in a table. Okay, back to the graph. I scaled my time axis, my independent variable. I'm going from 0 to 50. So 10, 20, 30, 40, 50. You don't need to go make all your ones in there. This is good enough. You can estimate for your graphing your points. Same thing on my vertical axis, my weight in grams axis. I just put 2,000 at the top because that's my biggest number. And then I divided it in half with 1,000. And then I just made my 4 tick marks in between that count for 200 each. I did not label all those. It's a lot of time, makes the graph busy. I know what they are. Anyone else can read the graph and know what they are. So if you haven't done so already, go ahead and plot your points. All right, let's see how you did. So check it out. I got my points: 0 years, 10 years, 20, 30, 40, and 50 years. Notice the 50-year one, we're at 6 grams. On this scale, 6 grams is basically on the horizontal axis. I've got my point a little bit higher, but if I was being super accurate, we'd pretty much be on the axis. So notice how when I connect up, I get this curve that's curving this way, okay? So it's getting less and less steep. Remember, the steepness is the rate, so the rate is decreasing as we march through time. Hence, we have exponential decay. So when you graph these, if it's a decay situation, your graph should show this kind of curve that's getting less and less steep. So curve gets less steep equals exponential decay. All right, now that you've watched the video, take a minute and jot down any remaining questions so you can bring them to our next class. Also remember, you can watch the video again. Maybe that will deepen your understanding. If you like the video, please click like and subscribe.